is Jack, and today we will study how heat transfer across a double pane window changes with increasing air layer thickness.
Double pane windows are two glass panes with an air gap in between them. The purpose of this air gap is to increase the resistance to heat transfer through the window. If we can increase the thickness of the air gap, we can get greater conductive resistance. However, we will also introduce convective heat transfer between the glass panes.
We will determine what type of heat transfer is dominant within the air layer and calculate the heat transfer across each window we study.
In conductive heat transfer, the heat is transferred by direct contact of two molecules through the vibrations of atoms using their kinetic energy. In convective heat transfer, the molecules close to the heat source are heated and flow upwards due to the lower density at higher temperatures. As the molecules flow upwards, they are cooled and flow back downwards. This creates a current of airflow between the glass panes.
It's so much warmer in here.
To test this experiment, 3 separate windows were constructed. One window was constructed out of 2 panes with no air gap to show purely conductive heat transfer. This acted as the control for our experiment. A second window was constructed containing a 1.75 centimeter air gap between the panes with a 6 millimeter thick wood frame. The purpose of this window was to show the effect of air insulating the window by primarily using a conductive form of heat transfer. A third window was constructed with a 6.2 centimeter air gap between the panes with a 6 millimeter thick wood frame. The purpose of this window was to show the increase in convective heat transfer in the air due to the larger air gap. After finishing the construction of the windows, the hot plate was brought to 50 degrees Celsius. Once a steady temperature was achieved, the window with no air gap was then placed on the hot plate. The temperature of the face of the window not in contact with the hot plate was measured every 20 seconds for 18 minutes to allow steady state to be reached. This process was then repeated for the other 2 windows. The experiment results indicated that as the thickness of the air layer increased, the overall thermal resistance also increased. However, using a 1.75 centimeter air gap produced a 5.65 degrees Celsius drop per centimeter of air gap, while using the 6.2 centimeter air gap produced a 2.34 degrees Celsius drop per centimeter of air gap. The efficiency of a thermal resistor may be defined as the temperature drop per unit length. With this analysis, the small air gap is much more efficient as a thermal resistor. As a chemical engineer, you can apply these basic heat transfer principles when designing any form of heat transfer resistance. Knowing the relationship between insulation thickness and resistance allows chemical engineers to design equipment that can perform under varying environments and spatial limitations.